We have this charge here, we have this charge here. Three charges, and in 2 dimensions, this is a question in 2 dimensions, so we're looking at the force on Q3 due to both Q1 and Q2. And we need to solve, firstly, the force on Q3 due to Q1, then the force on Q3 due to Q2, and then we have to add those forces vectorially to find the resultant force on Q3. I'm hoping that everybody finished this problem. So force is equal to K, Q1, Q2 on R squared, as we know, Coulomb's law. So I'll make a statement here. The force on Q3 due to Q1 first. Doing it in this format helps. For instance, when you're answering exam questions or test questions, it helps me or the examiner understand what it is that you're trying to solve at the time. So force on Q3 due to Q1 is equal to 9 by 10 to the 9, of course, times the charge of Q1, or we'll do Q3 first, is 3 millicoulombs, 3.0 times 10 to the minus 3, times Q1 is 2, thank you, 2.0 millicoulombs over R, the distance between them squared, 4.0 squared. Quick calculation will give us 3375 newtons, 3,375 newtons. Quite a large force. Force on Q3 due to Q2. K, Q3. I'm going to fit this 1 by 10 to the minus 3. Just fit it in there. Over the distance between them squared, 3.0 squared. Don't forget the squared, that's a common mistake. I think I've probably said that 5 times now. 3,000 newtons. Okay, so now we have to add them vectorially. Have a look at this diagram. It's actually a good diagram. Shows you this is the force due to Q2, because of course Q3 is positive, Q2 is negative, so it's an attractive force towards Q2. In this case here, Q3 is positive and Q1 is positive, so it's a repelling force away from Q1. And so that's how we get those two vectors there, or the direction of those vectors. Notice they've drawn these vectors relative to each other. Just this one here, just slightly larger, the 3,375 newtons compared to the 3,000 newtons. They're probably not proportional. It just shows that they are bigger. So I'll draw my vector diagram. You're often asked to draw a vector diagram. I wanted to, well, that's pretty straight, isn't it? I'll draw straight lines. Now, like most of the problems that you will see, it is a right-angled triangle. And we can see that here. If, of course, this is a right angle in here because it's a 3, 4, 5 triangle, then we have a right angle on the other side here because this is a straight line here. Okay, bisected here at 90 degrees, so bisected here at 90 degrees. Better draw arrows. A couple of people have forgotten in the test. I've I have started marking the test. Yes, I haven't finished marking the test. Don't forget to draw the arrows. Otherwise, I don't know what it is. It's just a line. It's not a vector if it doesn't have an arrow on it. I'm going to move this vector. I'm going to add these vectorial. I could actually move this one down and add them, or I could move this one up and add them. The last time I moved it up. I'm going to move this one down here. So same vector, just a different position in space. And then I'll label them. Labeling them is a good thing to do. This one's 3,000. 3,375 newtons here. They're of course at right angles. And our resultant R is this guy in here. That's kind of clear, isn't it? So how do we find this? It's easy enough. Using Pythagoras, we'll call this the resultant, R, little r. R is equal to the square root of each side squared, 3,000 squared plus 3,375 squared. I get a number here in the book, 4,515. 4,515 newtons seems reasonable. It's going to be longer. It is the hypotenuse. I'm missing something. That's right. You do need the angle because it is a force, a resultant force. They say force. You need to state the magnitude and the direction. Let's choose some theta there. Okay. This is, of course, is the adjacent side. This is the opposite side. Tan of theta. Adjacent. I beg pardon. Opposite over adjacent. And we should calculate that theta is equal to 41.6 degrees. Now, how are you going to state, let's go back to this diagram because it's easy to visualize. How are you going to state, because we've just resolved some vector in here, haven't we? Okay. It's going to be longer than that, but just for the purposes of explaining what's going on. And which angle have I picked there? I'll pick this angle here. Is that right? Theta. So if I've picked this angle here, how do I state that? How do I give that relative to something? We can't say below the horizontal here, can we? In the book, what they do, and you all, those people that are stating some ideas, they're valid ideas, they state them relative to the three charges, the line joining like these two charges, for instance. So look at the line joining Q1 and Q3, or the line joining Q3 and Q2. You can state it relative to that. And what they do in the book is say this. What do they say? The resultant force on Q3 is 4,515 newtons at an angle of 41.6 degrees to the line joining Q1 and Q3. Of 41.6 degrees to the line joining Q1 and Q3. Now, probably I still find this ambiguous. It's hard to understand. In all of the exam questions that I've seen, you don't have to. It's not ambiguous at all. It's usually below horizontal or something like that. Very easy to understand because otherwise the examiners would say, "Oh, which I don't understand which angle they're talking about exactly." And so then it's a do I give the mark or not? They want to make it very clear. Any questions about that problem there? I think that's reasonably simple for the quality of the answers that I've seen in the test so far for everybody here. I haven't done all of your tests, no. Go as fast as I can. Can I get a new page now? Anybody protest? Okay. 12. Yeah. Oh, what's that? I don't. Maybe. Yeah. If I have marked you, I've put it up on the Moodle. I've actually displayed those grades already. So some of the actually I'll just pause this. Some of the if we have two charges, quiet please now. If we have two charges, we say, and I've already stated this, that the two charges, whatever charge they may have, they somehow modify the space around each other, and we call this thing an electric field. The book actually here states the whole idea of two objects being able to exert a force on each other over some distance is fraught with philosophical difficulties. Does the electric field actually exist? What is it exactly? What is it made of? We just call it the concept of a field. So I'll state that. Mm-hmm. Yes. The idea that two objects may exert a force on each other at a distance. Boys, thank you. Idea of a field. So this, and I'll draw this in. I'll try and be consistent with how I draw electric fields. There's something that they do to the space around them. And I won't draw any directions yet or any magnitudes. Does anybody know how you display the magnitudes of these forces or these fields? That yeah, you can draw arrows like as in the directions. What about the magnitude? What's that? Sorry. Oh, okay. Yes, we'll talk about that in a second. Density of the lines, thank you, was what I was looking for. So if I put more lines in here relative to the other one, then this this charge here on the right tends to have a greater electric field around it. Okay, but we'll talk about it in detail in a second. Let's see. We'll go back to our text now. We'll just read this because this is quite interesting. Each charge in some way modifies the space surrounding it to establish an electric field in that space. Thus, when two charges are placed near each other, each charge comes in contact with the field of the other charge. It is the interaction of the field of one charge with the other charge that causes the force on the charge. Thus, instead of two charges causing a force on each other over some distance, we visualize the cause of the force to be localized action of the field of one charge on the other charge. It is the electric field at any point that produces the force on an electric charge placed at that point. We test the presence of an electric field in some region of space by placing a charged particle at that point. So let's give a visual representation of this. If I have some charge, we might say that in this case it's a positive proton, and there's a field surrounding this proton, and I'm going to draw it in. These field lines are directed radially outward. They meet the charge itself. They meet the source of the charge at right angles to that charge, and what we do is I don't know the magnitude or direction of the field around there. I'm just saying that there is a field around this positive proton. Okay, so I'll state that positive proton, and its field. How do I test the direction of the field? It's very easy. I place a small positive test charge in there. What is that test charge going to do? It's going to be repelled outwards, isn't it? So straight away, I can say, okay, the direction of the field is as simple as, in which direction would that positive charge Q go? It would go away from the proton. Okay, and so that is the direction of the field. The question is, which rarely comes up actually. Any questions about that? Why? Oh, yeah. Charge, yeah, okay, so the charge somehow modifies the field. Yes. Now all of a sudden, we don't have a small positive test charge, do we? We have this situation where there's kind of like the test charge itself has some field that's directed radial outwards from the proton, right? Ignore that. We call it a small positive test charge. It doesn't really exist. You guys ask, there's another class called metaphysics. Maybe you want to go and sit in that. Small positive test charge. Metaphysics is the philosophy of physics. Imagine, you all do mathematics, I imagine. Yeah. What is the definition of a point? You guys, yeah, okay. So, all right, we're talking about X and Y axes. X and Y axes, and I put a point there. There it is. Dimension. How is that possible, though? Yeah. Okay, so luckily for me, and luckily for me, I've placed the X and Y axis there, so I've given the point. some position relative to this x and y axis, and so I could measure it. I could actually say, oh well, it's x equals 4 and y equals 3, so that therefore it sits at 4, 3. We're not going to look at three-dimensional space just yet. But if the point just exists without the x and y axes, what is it? It's just no, right, so let's take it all away. It's yeah, it's a position, isn't it? We can state it as a position without length or breadth. So does it actually exist? Does the point itself exist? Okay. I've okay. I guess the point I'm trying to make is this small positive test charge Q with a little sub plus next to it doesn't really exist. It just tells me the direction of the field at that point. Okay, that's its only purpose. And so I can tell, yeah, the direction of the field at that point. If I want to show the magnitude, then yes, I have to draw more field lines. Okay. More field lines in here. The density, that's good. Density of the field lines. Give so the density of the field lines will give a visual representation of the magnitude of the field at that point. And it's kind of arbitrary. I've drawn more field lines in there, and those field lines only mean anything if I put them relative to something else. Um, a charge with less field lines around it, for instance. So here's some proton, positive proton. I know the direction of the field around it because of this small positive test charge. I know the strength of the field visually by the number of field lines that surround it, or the density, rather, of the field lines that surround it. Notice something also here. If I choose a point in space and look at the density of the field lines in that area there, and then the density of the field lines in the same area out here, what's the difference? Yeah. Just by showing this fact here, and I'm drawing this diagram for the purposes of this argument, so it suits me to put this box out here without any field lines contained in it, and it suits me to put this box here with 2 field lines contained in it. And this says that there's more density of the field lines the closer to the charge than there is further away out from it. Okay? So the electric field gets weaker as you move out, and you can see this. E, the electric field, equals the force per unit charge. Electric field, of course, now, as you should know, is a vector. Force is a vector. Charge is not. Charge doesn't have a direction. And E. E is the electric field strength. And can anybody see the units it has? Newtons per coulomb. Newtons per coulomb, yes. That's an easy one. So to measure the electric field strength at any point, we place a small positive test charge at that point. Okay, so this here, of course, the Q is that little charge. It's the force per unit charge, that says. The electric field strength is the force per unit charge. I hope this isn't too easy a question for you. It probably is. Have a go at this one, please. So that's the answer to one. That's easy enough. Remember, please. Remember to state your formula that you're using first in your exam questions. Most people have done that in the test that I've seen so far, which is good. And electron, of course, we've got the same force. We can rearrange for, so we have the strength of the field here. Strength of the field. What is Part 2, if an electron is placed at this point in the field, what force will it experience? We'll rearrange it, please. F equals EQ, 1.5 by 10 to the 4 newtons per coulomb. Charge, of course, is 1.6 by 10 to the minus 19 coulombs. Force is measured in newtons. What have I forgotten? Which is east. Let's picture it. Please. Thank you. Too much talking. Equals F on Q. We've got a positive charge. Some positive charge. Thank you. Boys. Boys at the back. Thank you. Positive charge. We have some field around it. We've just measured the strength of that field. Okay. Notice we measure the force on the small positive chest charge there, and we say the size of the small positive chest charge to get the electric field strength, force per unit charge, and then we put an electron in that field. So, well, the small positive test charge firstly looks like this guy here. Oh, it doesn't, does it? Right. Imagine though this here. It's going to make positive. Oh, it is. Yeah. Okay. Experiences a force due west. Okay. So it's experiencing a force in this direction. This is the picture that I'm picturing. Okay. So just for the purposes of we've answered the question mathematically. We can do. Let's picture it for those people that think in pictures. Okay. So here's that test charge. What if I put a little electron there at that point, in the same point there? Of course, it's going to be attracted to that charge, that positive charge, isn't it? And it's going to go in an eastward direction towards it. Okay, just for purposes of picturing what might be happening there. Okay. Electric field due to a point charge. Direction of the field. Okay, we've already done this. Direction of the force is the direction of the field at that point. Applying the above to an isolated point charge leads to the following. If the charge is positive, the field is directed radially out from the charge at all points. If the charge is negative, the field is directed radially inwards towards the charge at all points, as depicted here. So what we have is we have a positive charge. It might be a proton. If we were to put a small positive test charge in the area around the proton, then it's going to move outward, radially outward from it. If we have a negative charge here, so this is a little negative charge. If we were to put a small positive test charge in there, of course, it's directed radially inward. It's very easy to see that, and we can all see that. That might be why we're talking, because it's very easy. Magnitude of the field. To find the magnitude of the electric field at any point, we do the following. Place a small positive test charge at that point. Determine the magnitude of the force in this charge. The electric field strength E is given by the ratio F on Q. Applying the above to an isolated point charge leads to the following. Consider an isolated point charge Q. We wish to find the electric field strength at some point A, which is located R meters from the charge Q, as shown in figure 5.3. So this diagram here. So I'll draw this diagram in for us. Here we can explain this in, I'll just do it some charge. Some charge with, so it's a charge. And we place, what do they call that? QT. What do they call it? QT. Charge test. So that says test charge. Okay, so, all right. QT. Tiny little Q. Some test charge. It's located R meters from the charge. I better draw that a straight line. Yeah, all right. Laugh at my line. Yeah, it's all right. It is. Yeah, it was a stupid straight line. Okay, good. R meters from that charge. How do I find the force? I use this, of course, Coulomb's law, and from Coulomb's law, I can get, and using E equals F on Q, we're left with E is equal to K Q on R squared. So let's state that here. Coulomb's law. F equals K Q1 Q2 on R squared. E equals F on Q. And you can see quite clearly, if I substitute in here for F, thank you. If I substitute in here for F, we get E equal to K. Oh, I need more space than this. I'll go this way. E equal to K Q, one of the charges on R squared. So two ways to find the strength of the electric field. One using the force, and one using the distance between the force and the test charge. Okay, I expect they're probably going to give us an example here. Note that this formula enables us to calculate the magnitude of the electric field strength vector at any point. To find the direction of the vector E at any point, consider the direction of the force on a small positive test charge placed at that point. Okay, let's go to a new one. We're going too fast. Electric field strength calculations, point charge. Find the electric field strength E, 20 centimeters from an isolated charge. Q equals 4 microcoulombs. Let's picture it first. Q 4 microcoulombs, 20 centimeters from it. I'm going to say that this distance is 20 centimeters. It might be to the right. Centimeters. E. Have a go at that, please. Remove that. That just confuses us. Okay, of course, you should be getting used to this number. When we leave electric fields, you'll forget it again, but it is in your equation sheet. KQ, what is Q? 4 microcoulombs. On the distance between them squared. Nine by 10 to the 5. Newtons per coulomb you should have got. That's for part 1, and that's pretty straightforward. Part 2, at what distance from Q will the electric field be 1 by 10 to the 5? So E equal to 1 by 10 to the 5. 1 by 10 to the 5. Newtons per coulomb. R equals square root of KQ on E. Notice something here. What are we? We were 20 centimeters away. Now we're boys at the front. Now we're 60 centimeters away. We're 3 times the distance, aren't we? Can you see the connection there? 1 by 10 to the 5, 9 by 10 to the 5. Okay, it's a value of r 1 over r squared value. Okay, so they're proportional there. Okay, very good. You guys should be seeing that straight away now. Superposition of electric field is the next thing we will talk about, but we won't start that now because just make things, it's probably not necessary. Next lesson.